Now let's take an example to discuss this compound distribution where we'll try to use convolutions to typically solve for the aggregated variable. Now let's look at it. N takes the values 0, 1, 2, probability 1 by 2, 1 by 4 and 1 by 4. These are the probabilities. Okay. So the probability of n equal to 0 is 1 by 2. Probability of n equal to 1 is 1 by 4, and the probability that n equal to 2 is also 1 by 4. Fair enough. And xi's have a uniform distribution between 0 to 10. So if there is no claim, there is no question of xi. So here xi is 0 itself. So this is the probability and these are the possible xi's. Whereas in this case, yes, it is xi is having a distribution uniformly distributed between 0 and 10. Here there are two independent x and y, two independent uniform distributions, x1 and x2. So x1 is having a uniform distribution between 0 and 10. x2 is also having a uniform distribution between 0 and 10. So probably I can call something as y. Y is probably x1 plus x2. That is what I can look at here. Here the probability is 1 by 4 uniform between 0 and 10. So I can find out the frequency distribution of S in this case, and probably I will also try out finding out the frequency distribution of S in this case. Now wherever we have this kind of a distribution, the summation, we can very well, if I am assuming that this is Fy is the density function of y, then fx1 is the density function of x1 and fx2 is the density function of x2. We can very well express the fy, the density function of f, as an integration in terms of both f of fx1 of x1 and multiplied by fx2 y minus x1. This is a typical fundamental of convolution, right? So I can very well use this fundamental of convolution to try to see how the graph varies between 0 to 10. So if it is for the first one, it is 1 by 10, right? If it is for one claim, it is 1 by 10 across. So probably 1 by 10 and there is a 1/4 probability. So 1 by 40 is going to be the possibility. So basically it would have been the case that at 0 the probability is half, right? If I am just looking at it at 0, the probability is half, and between 0 to 10, because it is uniformly distributed, the probability is 1 by 40, because 1 by 10 at each and there is a 1/4 chance of occurring. So 1 by 40 is the probability across, right? But now I have to look at even in the second case. That's the reason for the second case I am looking at the convolution part. Okay, x1 plus x2, which I am taking it in this way, and this I am integrating it between minus infinite to plus infinite. Now fx1, I know it's a uniform distribution between 0 and 10, and because it's a uniform distribution between 0 and 10, I can very well integrate, I can very well take the fx1 as 0.1 times fx2 y minus x1, right? Now I know y value can lie anywhere between 0 to 20, because it's a summation, the maximum it can lie anywhere between 0 to 20. So this part is coming out as integral minus infinite to infinite. What is the density function of this? The density function of this is 0.1 times fx2 of y minus xi. And now this actually will get changed into 0 to 10, because this value fx, if xx1 of x1 is having a value of zero point 0.1, when 0 is, when x1 is lying between 0 and 10, and it is having a 0 across, which means this integral can very well be refined into integration between 0 to 10 zero point 0.1 times fx2 y minus x1 dx. Now we know y minus x1 also will lie between 0 and 10. Y minus x1 will lie between 0 and 10, but y can lie anywhere between 0 and 20. So which means this is actually getting split into two scenarios. Between 0 to, if y is lying between 0 and 10, right, if y is lying between 0 and 10, probably y minus x1 is actually lying between 0 and s, the y, 0 and y, right. If y is lying between 0 to 10, so I can very well transform this. Let's say y minus x1, I am directly changing it. So this I am changing the limits from, let's say, 0 to y. There was a zero point 0.1, and now this also, between this, it is a zero point 0.1 itself, zero point 0.1 dx1. So it is becoming 0.01 y. So when y is lying between 0 and 10, when y is lying between 0 and 10, the integration is 0.01 y. Similarly, there is a possibility that y can lie between 10 and 20 also. When y is lying between 10 and 20, I see that the limits here will change from 10 y minus 10 to 10, right, because y minus 10 to 10 is something, it can go anywhere between 0 to 10. So this is again coming out as 0.1 times 0.1 y dy. So 0.01 times, sorry, 0.01 dy. So this becomes some probably y times 10 to y minus 10. This becomes 0.01 times 10 minus y plus 10. So 0.01 times 20 minus y, which comes out as 0.2 minus 0.01 y. So between 0 and 10, okay, now it comes like this. Between 0 and 10, the function is 0.01 y. And between 10 and 20, the function is 0.2 times, sorry, 0.2 minus 0.01 y. Now let's look at it. When n equal to 0, I am seeing that the probability is half, but the overall so the graph comes out at n equal to 0, the probability is 1 by 2. N equal to 1, which is the probability of 1 by 4, I see uniform distribution between across 1 and 1 by 40. Now when I see n equal to 2, I see a number 0.01 y. 0.01 y between 0 and 10, which means if I am looking at y anywhere between 0 and 10, so it becomes 0.01 added. So 1 by 40 was earlier with this claim. Now I am getting 0.01, 0.02, 0.03 up to 0.1, and this is having 1/4 probability. So it becomes 0.025 and so on, it gets added up to 1 by another 1 by 40, right. 0.1 by 4 is 1 by 40, and whereas this one is 1 by 400, 2 by 400 and so on. So by that much extent we see an increase to this. Between contribution to the second one is getting an increase, because to this number 1 by 40 plus 1 by 400, 1 by 40 plus 1 2 by 400, it goes up to 1 by 40 plus 1 by 40, which will take me to 2 by 40 or 1 by 20. So this is where I have 1 by 20. So from here I see a line going from here to here. Then what about between 10 and 20? I am seeing it as 0.02, sorry, zero point 0.2 minus 0.01 y. So if y is 10, it becomes 0.2 minus 0.1, which is 0.1. So zero point 0.1 is nothing but 1 by 10, right? 0.2 minus 0.1, so it is 1 by 10, which will go somewhere here. This is 1 by 10, and from there 0.2 minus 0.01, 0.19. So from 0.19 it goes up to, so zero point 0.2 minus 0.01 times 10, which is 0.2 minus 0.1, which is 0.1. Then 0.2 minus 0.01 times 11.11, which comes to 0.09. So from here you see a gradual fall, because when y is 20, 0.2 minus zero point 0.2, which becomes 0. So the typical graph comes like this. Between, so when I am looking at the claim 0, 10, 20, at 0 the probability is half. When I am looking at only the second one, this is the line at 1 by 40. When I am looking at only the third one, 0.01 s. So 0.01 s, if I am simply looking at s, when s is 0, it is 0.01 times 0, which is this one, and when s is 10, it is zero point 0.1, and that is multiplied by 0.25, because 1 by 4. So again this would be a line only this much between 0 and 10, and between 10 and 20 I see when it is 10, zero point 0.2 minus zero point 0.1, so it is somewhere here, and from here I see a line like this. But these two need to be added up, so that is what is resulting in a line like this, wherein 1 by 20 is getting created here, and after that again it is coming out something like this. So this is the traditional graph that I can very well associate with the frequency function associated with these three types of claims. So here we have an individual blob here, because there is no distribution, because no claim at all in the process, right?